So let me just go back and rewind this and look over what we were talking about. So I can do a sort of fast track of what we have been doing and explain a little bit. I think that gives us like 30 minutes or 25 minutes. And then we take up from where we stopped yesterday. So we're looking at a few problems in free boundaries with a bunch of applications. And these are applications I just wrote down, but there are thousands of more applications you can really find in the literatures, and or you can cook it up yourself. So we went through the modeling. We saw a lot of different models, and I think we arrived all the way here to non-degeneracy. And we did non-degeneracy, so existence, optimal regularity, and non-degeneracy. And we will be continuing after coming back in 2 hours or something from Hausdorff dimension. And so Hausdorff dimension, you can think of that what you're saying is that the surface, the free boundary, is like a surface. That's what you're saying. It's like a real surface. But of course, still, Hausdorff dimension being finite doesn't mean that your surface is good enough. It can be very nasty. And I just give you an example of how nasty it can be. Think of something like this. So these are all small balls, and it can be lots of other balls, smaller balls around this. And then, so these are all small, tiny sets when the function is 0. So u is 0 on the white side, and the white part. So these are all small holes here. So this can actually be a free boundary. You don't know that. At the beginning, you don't know that. And it can have finite Hausdorff measure, n-1 Hausdorff measure. So, and if you take this, and you see that actually there's a tangent plane also at this point. If you blow it up, that we did yesterday with the function UR, scale it, and you scale it, then you will see the whole picture will be something like this. That is a free boundary. And still is sort of, this still is so nasty that you cannot even say anything about it. What I'm intending to say eventually, the last day here, is that this actually is not like this. It is locally, if you take any free boundary point, locally it's a very smooth graph. What happens later, I don't know. But here, locally, if you assume something about this, then locally it's going to be a very nice graph. Here the function will be 0. Here the function will be positive. So there is a normal vector, and here it's a graph. So gamma will be locally like x times the normal vector is equal to some function of x prime. And x prime is in this directional, only the tangential directional vectors components. So this is what we want to say eventually, but just realize that actually it has all possibilities until we have come to that point. Also, what you will eventually see that there are actually problem examples, and it can happen that the set coincidence set when the function touches 0. It can be something like this, and actually there are examples. You can do that. And then it finishes here. And then it might be also something like this. And it finishes here. And these are examples you see that the free boundary is not really like a graph like this. And it can actually happen. Just to see, but this example is a little bit harder to give. This one is a little bit harder. Actually, there's cardioid type regions. There are explicit examples that the free boundary looks like this. It's not a graph. There are also, but to see an example like this, you can just cook it up by take a ball of radius 1, put boundary data here, so that you get the solution, which is like a sphere. Put boundary data exactly for the sphere one. I gave you one example yesterday with this Laplacian of use the characteristic function minus the max. That actually can do it here. And then you just reflect it on this side, and that will also be a solution with the boundary values. But this already gives you a point when the free boundary is not regular. So give this example, or whatever example you want, it doesn't really matter. Give any example of free boundary which is smooth. And suppose locally here is convex, you can find one at least which is convex locally here, and then you can reflect it. Here is positive here, and this is just the reflection of here. It's even reflection. And you see that this is an example of a cusp. Of course, this is not naturally made. It's sort of, we just force it to be like this. And this gives an example of cusp point. You can still say something about cusp point, but this is not the topic of this lecture. You can still classify all these points and look at singular points, etc. So we stop here basically, and we will be continuing very soon. And these are all you see here, especially here, monotonistic order and global solutions. These are techniques that we will be using. And you will see, you will actually be exposed to very recent techniques, like what people developed in the last 10 years. And this is very fresh frontier of research. I will not enter into this. Maybe last day I will say a little bit about these things. We shall see how time is with us. So we looked at the several problems, free boundary problems. We started with looking at free boundary actually can occur in general. A simple case is when you start playing with the Dirichlet problem and putting extra data, then it is not solvable unless you make some other things free. When you solve the Dirichlet problem, then everything else is sort of fixed. You cannot go and influence it and change it. If you change it, then you have to change something else to adjust it. So let me go further. Yeah, and then we saw that examples like this, when you it's a heat flow, so you have the heat is affecting the iceberg here and tries to melt it, and there is a balance of the energies inside the ice and inside the water, and there's a sort of kinetic energy or latent energy exactly in the frontier of ice, and that energy is sort of, it doesn't come from anywhere, it's a molecular energy sort of, and it affects the moving of the boundary. So there is no external force here. So the force is coming from actually within inside. So you give, initially you give something and the force is already there, and that force starts moving everything. Okay. And we talked about lots of models. Specifically, we talked about the show flow, which I showed you sort of in a show flow when two plates are pushed and material is driven with this force. And we did this integration by time, added up all the pressure. So this is accumulated pressure. U is the accumulated pressure. G is kind of pressure. It represents pressure. And the great G is maybe the pressure. So what you do is you do it like this in order to solve that problem, which is at the beginning is not a mathematical model but physical model. You want to solve it. What you do is that you see, okay, that problem is not even defined because you're talking about things that are driven by the gradient of the G on the boundary, and that boundary might not even be having it so that we don't know at the beginning to even have a normal vector. So this is not well posed problem at the beginning in the sense of it's not well defined. So what we do is try to solve it some other way. And we come up with the idea that we can actually integrate this. In time, the problem you get is much more solid and solvable. It's a variational problem. When you solve this problem, you see that your solutions is not going to be C2. We saw that. It's going to be C11. So if you take, then it means basically that the Green's function is not necessarily C1. So in general, the Green's function is not necessarily C1. So that means that this is not defined. So somehow the problem is a little bit diffused. I mean, you don't really understand the problem. But what you say is that, okay, I can solve this problem in a weak sense. And in a weak sense, the best way you can come up with is to solve another problem and say, okay, when this is regular, this is the same problem. So you solve it in a weak sense. There are actually solutions to the original problem when they use implicit function theory. So they prove existence. If your initial data domain D0 here is smooth, then you can, for short time, solve it with the implicit function theory, or maybe other methods, I don't know. But implicit function theory might be able to solve the problem. And there are some solutions of this problem. So they prove existence of a solution for short time, because as time goes, then the solution is not necessarily smooth because of the example I just told you about. So if you start here, your region is something like this. This is D0. If you start solving your problem, let me even make this. When you solve your problem, initially this is smooth, you can solve it, let's say. And you see that the solution would be something like this. This is dt. When time goes, then these two will meet. At some point they have to meet. Now this is the, let's say, t1 next time. And at this point, the solution doesn't have a classical meaning. Okay, so you cannot say that this is solvable in C2 sense. At that point, all of a sudden, the graph is not really a graph, and then it jumps. Next step would be that you get, so if I just take the same picture here. So next step here, d time 2, let's say this is time 1, time 2, and time later on, time 3, which is a little bit later, is that the solution will be something like this. So it breaks. This piece that is inside, it will separate it. And this will be like this. And then you see that this might be still smooth and solvable, and you can continue. But at this stage, there's a stop. And then at that stage, you cannot have a reasonable mathematical formulation. This actually happens a lot in moving of surfaces by mean curvature flow. So those problems are quite well studied and very interesting techniques, actually, and very deep techniques.
This is what they even for like point correct conception that they study development of singularity.
Yeah. So well, sort of related. Yes, for minimal, yeah, sort of related. But not exactly. This is a little bit. I mean, I'm not interested about singularities. I'm interested about solution in classical sense. So what they do in minimal surface theory is that they sort of they jump. They do surgery and they jump. They jump over this and they say that the solution can still continue. At that time, there is a surgery, so they take a small piece out. It's actually a real surgery. You're going to take a piece of this out and then work with it. It's a very interesting technique. I was actually suggesting with last year to one of the people in the minimal surface theory that maybe that technique can be adopted here, and that was we talked about it an hour or so, but then none of us came back to it.
That's what I thought. Like once you mentioned it, I said that
this is because I heard the talk of Yuskin, and he was giving several talks at KT, and then we talked after that.
I think it should be because
I think it is doable. Nobody has done it, but it's definitely doable.
When it separates, it's like
When it separates, you're okay.
yeah.
So after separation, you have to do the surgery, somewhat defined. Surgery here means a mechanism, okay? But the reason they call it surgery is really they cut it.
Yes.
They cut the piece, and that's the reason they call it surgery.
Yeah.
So you have a mechanism of sort of getting past that point that two surfaces meet, and then there is no definition, then classical definition. Okay, think like this. I mean, at the calculus level, you could think like this. If you have two curves, so this is y1 is f of x, and then you have another curve, y2 is f of 2. You can define them separately. But when they meet each other, then still here is okay, you can define it. But then one goes above this and the other one goes below this, then you go on to define it. It's a little bit more troublesome now. They define it not like exactly like curves in this way, but locally they have relations to each other. So that means that at that point there's a trouble, so you have to do a surgery and jump over that stage. So they did it very well. And I still don't know the techniques, but I'm pretty sure that that technique has a good chance here.
Because it is quite well done PDE technique.
Yes.
I attended lectures in Bangalore,
Uh-huh.
and it's not much of hand waving. They have very.
Oh yes, it's not hand waving. They're very precise. I agree.
Your topology thing is hand waving, but what Besson.
Okay, yeah.
He gave series of lectures after in Bangalore, IISc Bangalore, which I had attended, and it was very precise.
They're doing PDE basically. PDEs are usually very accurate.
So it was very and this is slightly simpler, I think.
But this model, this is much simpler. Because
so
singularity here is very obvious.
Yes.
Because I think we have good classification of singularity. Well, not exactly, but we have good classification. I think there's one. Well, this is something maybe I will talk about the last stage singularities, because you can have singularities in this problem, and classifying singularities is not clear yet. So if you have a cusp like this, so how is the asymptotically the cusp look like? How does it look like? And then what I mean how it looks like, it means that if you just zoom in, but somehow scale it, and there will be some resemblance of some pictures. And actually the answer is, which is not, the conjecture is that asymptotically they are ellipsoids. So what happens if, let's say in two dimensions is clear, because it's just things like kind of two curves, and then if you scale it correctly, it will be, you can separate them. You want to keep in the end still separated, so it doesn't go to a line. So scaling a little bit differently, you scale faster in this direction, slower in this direction, you can keep the distance, and then it will be two lines. In 3 dimensions, you do the same, faster in this direction, slower in this direction, it gives you actually a cylindrical ellipse, actually. The base will be ellipse. I think in 3 dimensions that is okay. There is one problem, and in any dimension, there is one problem that it also may appear that it's a paraboloid. And that we cannot exclude, and I don't think we should exclude it, because paraboloids are actually obstacle problems, solution to obstacle problem. And we have been trying to do that, I think, 20 years now, but we still have the parabolic problem, parabolic shape clear. I've talked probably to too many people about this, but no one has any idea. We are doing some work on this with Jörg Weiss in Germany, and but I think we are close to it, but I'm not sure. So the paraboloids are what is left, basically. Otherwise, ellipsoids are easy. We have a very nice classification that we can really take. Asymptotically, they are ellipses or ellipsoids, and we can in one direction. So ellipsoids in one direction, and then they change. Asymptotically, they change. When I say it's ellipsoid, it's a perturbation of ellipsoids. So it's a graph. It's very close to ellipsoids, and asymptotically, they are ellipsoids that are given through the blow-ups of that point, and when you blow it up, it will be polynomial. Solution will be polynomial. U will be a polynomial, actually. The function U will be a polynomial blow up. That polynomial will give you the axis of the ellipse. It will give a very good representation, very perfect and clear representation. Of course, this is a little bit deep water, but so let me do a little more things before they come and pick me up here. And then we modeled this by and said that you can really solve with this with the variational way, and we connected it to the problem G, and finally, yeah, so we connected to the function G in this way. And a little bit of connections to stochastics, which we didn't go much deeper, but there's a lot of development in this. So let me go further fast from the applications to mathematical theory. Okay, what we did here is existence and uniqueness, and this was something you have to practice on a little bit more and work with the details. So hopefully today I don't know, I'm going to give a little bit more, let them practice on this. So you have the exercises and which is also part of your exam, I guess. It's gonna be to work on it. And yeah, this was interesting. This optimal regularity. So we saw, I think, 3 techniques for optimal regularity, and I'm going to do one more before we finish. And you will see the power of that one. There's another one that is much more complicated. I'm not going to do that, which is used for fully nonlinear PDEs. Which is extremely, it's a very simple idea, but extremely complicated even to think about it. And that was actually created, that example, which finally solved many problems, was created by one of my former students, John Anderson. He had a brilliant idea of the dichotomy. And when he came to me and said that this seems to be true, and this was in 2011, we were at MSR. I didn't believe that there's no way to be able to prove this. And then me and Eric Lindgren, another former student of mine, were sitting a week and reading his short notes just to understand and to start rephrasing a little bit, and that was correct. And he had a very beautiful proof of regularity theory for not this problem. This is just one of the problems. He had a very bunch of problems, and then eventually you can actually extend it to fully nonlinear problems that we did with some other partners. So I'm going to give you one further, which is not that one, but using monotonicity formula, because you like monotonicity formula, and you want to see that. And you will see that proof is actually elementary. So, but there is a tool, there is a hammer, let me call it a hammer, that you have to have the hammer. Proving that hammer is very hard, that the hammer exists and you can use it. Once you do that, you have this hammer, you can use that. Well, I'm saying hammer, real hammer. It's real. You just pound on the problem and it breaks it and solves it. It goes in one line basically. So I will do that maybe today actually. When I come back, I can show you how it works. I can write one line and that's the proof of it. But then you have to accept one point of an inequality, and that's the monotonicity formula. If you accept that, that is a completely different thing, which is a tool that I'm using here. And then the whole thing is the Fatou lemma, and then that inequality. Then you get that the functions, any solution to PDs of this type, no sign, nothing, I can show you that it's C11. And you will be surprised with seeing how powerful that tool is. Okay, so I think I will finish here. And
So I think we need to reschedule a little bit because
yeah.
It seems you may be arriving around 2 o'clock.
2 o'clock.
Yeah, so it's okay. That they're like maybe it's fine. I will take the class whatever, and whatever if time has to be adjusted, we adjust it with my talk tomorrow.
Okay. Good.
Just to have the time schedule matched.
Okay. All right, so see you later.
That's my wife. PDF.
Okay, see you later.
Second,